Very good. So I think we should get started. I wish you a beautiful afternoon here in Munich. I'm super happy that so many people found their way to my session about understanding and applying embedding vectors in AI solutions. My name is Stropek and I will quickly introduce myself. I myself am a passionate software developer. I love to write software. I have been writing software for the past 30 years. I'm an IT entrepreneur. I run my own little company, which is called Software Architect. And besides my professional work, I also do a lot in the area of teaching and mentoring. I am chairman of the local Coder Dojo in my hometown, Linz. There's a programming club for kids. I teach at a local computer science school 1 day a week. So I love talking about technology and I love applying technology. And in the last year, artificial intelligence really became a very important part of my work, and I think I'm not that different for all of us because AI has become a super important part. And today I would like to introduce you to the concept of embedding vectors. I'm going to demonstrate a large number of samples. Yes, we will mainly focus on code, but don't worry. If you are not familiar with code, if you do not regularly write code, you will definitely understand the few lines of code that we are going to write. They are not complicated. I'm absolutely sure that that will not be a problem. This is a conceptual talk. This is why I called it understanding embeddings. So don't worry, we will not go too deep. Now, as I mentioned, I will demonstrate a lot of examples in my talk today. So I created a Python notebook. It's available on Google Colab. So if you would like to have the Python notebook, which also contains a link to my slides, just take a picture or write down exactly that URL, and here you can find all the details, all the code samples. So you do not need to take notes. If you find something interesting, you can always use this link and try all the samples at home. All you need to try the samples that I'm going to show you is an OpenAI Pro subscription and the possibility to use the OpenAI API. The notebook contains a link to the website where you can get an API key. Just throw in your API key and you can do all the examples that I'm going to show you in the next 45 to 50 minutes. I try to finish early so that we have a little bit of time for questions. Speaking about questions, don't hesitate to raise your hand if you have questions. If you want me to clarify something, don't worry, let's make it interactive. We are a pretty large crowd here, but your questions nevertheless make the session more relevant to you, and maybe other people are also interested in what you are thinking. So don't hesitate, raise your hand. I'm more than happy to take questions during the talk. And with that, without any further ado, let's dive right into it. Now, first, I would like to talk a little bit about what embedding vectors really are, because I guess some people here in the room have maybe heard about the term, but have not a really clear idea what embedding vectors are. Let me give you an example. It is somewhat comparable to OpenAI embeddings, but I will talk about the comparison in a second. Now think about if I gave you the following task. We are a large group here in this room, and I ask you to group all the people in this room by personality. How would you go about that? Well, probably you would go around the room and ask questions. For instance, you could ask questions that allow you to understand how open certain people are to new experiences. To make this somewhat processable with a computer, you use a number. Maybe a number between 0 and 10, or maybe a number between 0 and 1. Use, for instance, a real or float value, something like this. And then you take this number and you draw this number on a line. You simply say, okay, somebody said 5 or 50 or whatever range you use, so you have a, let's say, one-dimensional vector, something like this, that reflects the answer of the user. Now you ask a second question, maybe about agreeableness, and then you get a two-dimensional vector depending on what the person said. And you can go on and on and on and on, and at the end of the day you have a multi-dimensional vector. Every number in this multidimensional vector represents a certain property of this person, okay? So that's the idea of an embedding vector. You essentially take something which is, well, hard to express in numbers, and you make it expressible in numbers in the form of vectors. Now, this is a very simple analogy compared to what embedding vectors in the context of AI really are, and therefore, let's take a look at the real world of embedding vectors by taking a first look at the prepared code. If you are not familiar with the environment that I am in here, this is Google Colab. Google Colab is a free website where you can create your own Python notebooks. You can enter some Python code there and you can run it. Of course, you have limits in terms of memory and CPU and things like that, but at the end of the day, for experiments with OpenAI embeddings, this environment is perfect. You do not need to install Python, you do not need to install some web servers, simply go to Google Colab and do some experiments. And this is exactly what I prepared for you today. Well, the first thing that I did in this Colab notebook is I installed the OpenAI API. I'm going to use the latest version of the OpenAI API. I ran this cell prior to this talk, so I do not need to run it again. Just trust me, the OpenAI API is installed. Now let's scroll down a little bit, and I would like to jump over that for a second and go down here and show you how it works if you want to get embedding vectors from OpenAI. This talk will be specific about OpenAI embeddings, but the general concept of embeddings is applicable to pretty much all the large language models, okay? But let's take a look at the OpenAI API. Well, the first thing that you need to do is you need to specify your OpenAI key. If you're using Azure OpenAI, you do not need to specify a key. You could also work with an Entra ID principle, Azure Active Directory, or a managed identity, which is probably more relevant for the enterprise customers here in the room. You don't want to use API keys, right? Because they can get lost. You maybe check them in, or somebody, I don't know, posts them on X or wherever. You don't want to have that. So use Azure OpenAI managed identities or certificates or something like this. But here I'm using the OpenAI API directly, and they only support API keys. Okay, so this is what I do here. Now, if you want to calculate an embedding vector for a text, what you have to do here is you simply specify the text here, and then you call the OpenAI client with embeddings create. Very simple. There is a REST API too, so if you do not want to use Python, you can obviously use some other APIs like Node.js, .NET, Go, whatever. And if you have a programming language for which there is no API, absolutely no problem, simply call the REST API. Then you have to specify a modal. And this is the first very important concept here. Calculating embedding vectors. What I mean embedding vectors are, I will talk about that in a second, but it is currently just a collection of a lot of floating point values, okay? Calculating the embedding vectors with OpenAI is not done with the ChatGPT model. The ChatGPT model was optimized for generating text responses in a conversion style, okay? But these models, they were optimized for creating an embedding vector. Now, we have this elephant in the room. What is the embedding vector at OpenAI? The embedding vector at the end of the day is similar to what I told you about this personality analysis. It takes a text and tries to embed the content, the context of the text into a large number of floating point values. So you take a sentence, and what you get back is some thousands of floating point values, and they are representing the content of the text. So if you take two texts, then you get two n-dimensional vectors. You can compare them, and based on the comparison, you get an idea how similar they are. And we are not talking about formal similarity like with something like the Levenstein distance, where you compare the number of insert or removal or move operations that you need in order to get from one text to the other text. It is really a comparison based on the content of the context of all these words. I will show you a lot of examples later on so you really understand what I mean with that. The single values on themselves, if I take, I don't know, the 716th floating point value of this vector, doesn't tell you anything about the text. So it's not like in our previous example where I know that the first value in the vector says something about the openness of a person. That was true for my very, very basic sample at the beginning, but this is not true for embeddings. The single value of a vector, of an embedding vector, doesn't tell you anything. You have to take a look at the entire vector. So you see the API is not really complicated, so let's try to get such an embedding vector for the word K. Now here we can specify any sentence that we want. Should we change it? Of course we should change it. Let's say the OOP conference is awesome. So let's try to calculate the embedding vector of that. I will simply run the cell and you will see that we get back, I will zoom in a little bit, we get back a vector with 3072 dimensions. And here I have very interesting and brand news for you. A few days ago, I thought I was very well prepared for OOP conference. And you know what happened 2 days ago? OpenAI published completely entirely new embedding vector models. Oh, I was super happy. I was sitting at home and I thought, oh my God, that will be a long night prior to OOP. And yes, I spent a long night to update all my samples. I did that. So what you see here is the latest and greatest model for embeddings that OpenAI released the day before yesterday. So the day before yesterday, OpenAI released completely new embedding models. They are the version 3 of the embedding models. Prior, we had the version 2, the ADA 2 version, but this is now the version 3 of the embedding models, and I am using the large one here. There is a small one and a large one. The small one is way less expensive than the old version 2 and super fast. The new large one is a little bit more expensive than the old version 2 one, but it is much more powerful and more intelligent. So now you have the choice with version 3 if you want the best text understanding capabilities, then you have to pay a little more, or if you want something that is small, that is fast and that is cheap, if that is enough for you, then you use the small model. I'm using the large model here and therefore the vector is 3072 dimensions long. Maybe you have worked with embeddings before in OpenAI, then you are used to 1572 dimensions, but this is no longer the case. There is another very important aspect of the new models. If you want to use the new models, the large or the small models, but you have to process them and store them in a system that has very limited memory and processing capabilities, you can now ask OpenAI to reduce the number of dimensions for the embeddings. Then your results will be a little bit worse, but not significantly. So you can, for instance, say, I want to have the large model, but please only give me the first 1000 dimensions, which are most important for the context, for the content of this embedding. And that allows you to use these embeddings in scenarios where you, for instance, have a vector database that only supports 1000 dimensions in a vector. Okay? So this is also a new feature that came out the day before yesterday. Now you understand why we have 3072 dimensions in this example here. Now let's take a look at such a vector. Here you see the first few numbers from a vector. And what you see is that each number in the vector is a value between -1 and +1. This is not a percentage value. It's just a value between -1 and +1. This is what this contains. The last example, and let me show you that with a different color here. The last example is I'm calculating the norm, let's say the length of this vector. Yes, mathematics, you can calculate the length of an n-dimensional vector. And what you will probably see is that the OpenAI vector length is normed. We say it is normed because the length of every OpenAI embedding vector is 1. That will be important when we do some calculations for AI-based applications. Keep that in mind. the length of every OpenAI embedding vector is always 1. So you do not need to normalize the vector in order to compare them. I will go into more details later on. So now you saw an embedding vector. Good, very good. What can we do with an embedding vector? We can compare embedding vectors. Looking at one single embedding vector is worthless. It doesn't tell you anything. You cannot get back or recreate the content of the original text by taking a look at the embedding vector. That simply doesn't work. It doesn't work like that. It's similar to a hash function, if you want to put it like that. Okay? Somebody once told me it's like you can create a chicken McNugget from a chicken, but you cannot create a chicken from a chicken McNugget. I'm a vegetarian, so I'm not interested in chicken McNuggets, but I think you get the point, right? Important is that you can compare these vectors. And for that, I need to remind you a little bit of math. Yeah, I hope you like math. It will not be complicated, don't worry. We need to find out how we can compare embedding vectors in an n-dimensional space. And the most important KPI for comparing embedding vectors is the cosine similarity. What does the cosine similarity mean? In German, we're here in Germany at this conference, it's called the Cosinusähnlichkeit. What do we do with the cosine similarity? Essentially, we compare the angle between the two vectors. Let me show you a diagram. I will have to run this sample code here, and that will give me 3 diagrams, hopefully. Here they are. I will zoom in. Imagine that you have a base vector. This could be the embedding of a user input, for instance. And then let's take another color. This might be the embedding of a document inside of your knowledge base, for instance. And now you would like to calculate the cosine similarity. We already know that the vectors always have the same length. So we do not need to compare the length of the embedding vector, because I told you embedding vectors in OpenAI are always normalized to 1. What we need to compare is the angle between the two vectors. Now, if we have two vectors which end at the exactly same point, then the cosine similarity, the cosine of the angle 0 will be 1. 1 meaning these two vectors are identical. Now, if we have something like this, where we have, here you see it, an angle of 90 degrees between the vectors, the cosine similarity will be the cosine of 90, which is 0. If we have an extreme situation where the angle between the two vectors is 180 degrees, we have a cosine similarity of a cosine of 180 degrees, and that is -1. And now you understand what these values mean. The cosine similarity of two vectors is simply a value between -1 and +1, representing the angle, the difference of the angle between these two vectors. Now this example here, as I said, you can try it at home, it's in the Google Colab, and this example is only in a 2-dimensional vector space. But the math in n-dimensional vectors is exactly the same. And for that, I will quickly go back to my slides and look up the correct slide that I wanted to show you. Yes, this is the correct slide that I want to show you. And here you see the formula with which you calculate the cosine similarity that you use in your enterprise AI solutions. What you essentially do in order to calculate the cosine similarity is you multiply the two vectors using the dot product, skalare Produkt in German, okay? You simply take the first value from the first vector, multiply it with the first value of the second value, and add the second value of the first vector with the second value of the second value. I think you got the point. You do that in a loop. So essentially, you do 3072 multiplications of floating point values and calculate the sum. That's this part of the equation. Now, the lower part of the equation, luckily, is irrelevant when we talk about OpenAI. Why? Because this is the product of the length of both vectors. And what did I tell you about the length of the vectors? They are normalized. 1 multiplied by 1 is 1. Something divided by 1 is something. So therefore, we can simply ignore the lower part here of this equation. So what we end up with in the context of OpenAI is the similarity, the cosine similarity of two n-dimensional vectors is the dot product of the two vectors. And this is a super, super important concept that you absolutely have to remember if you want to program with AI solution with embeddings. Okay? That's the point here. So let's go back to our code. This, by the way, this sample code here is nothing special. It simply calculates a bunch of two-dimensional vectors and uses matplotlib here inside of the Colab to generate the diagrams. This part of my example has nothing to do with OpenAI. It's only used to generate 3 diagrams in two-dimensional vector space. So don't get me wrong, this has nothing to do with OpenAI. Only the samples down here, where we really call this embedding stuff here, this is OpenAI. Now, if you take a look at this one here, this example, of course I'm not, or the next example, of course I'm not going to calculate the cosine similarity on my own by doing a loop over the elements of the vector. Because you should use existing math libraries because they are going to use hardware capabilities of your CPU and or your GPU to quickly calculate the cosine similarity. Those hardware mechanisms are super fast in multiplying floating point values. You probably know that. So please do not, I mean, it's a good exercise. If you want to calculate the cosine similarity on your own, just do it, but don't do it in real life. This is something where there has to go a lot of brain power into it to make it really, really fast. Because in reality, you do not compare 2 vectors. You compare a million vectors, and that has to be pretty, pretty fast. Now let's think about, from a content perspective, what these embedding vectors really are. And I would like to scroll down to this example here, run it, and then we are going to take a look at some examples, okay? It should work. Let me see if we get an example. Yes, we got an example. That is good. Let's take a look at the first example. I will not zoom in. I hope you can read the text even from the back of the room. I will read it for you if it is hard to read. Here we compare 3 sentences that I prepared. The first one says, I enjoy playing soccer on weekends. The second one says, football is my favorite sport. Playing it on weekends with friends helps me to relax. And the third sentence is, in Austria, people often watch soccer on TV on weekends. I'm from Austria. This is why I used Austria here. So guess which similarity, which sentence is more similar to the first one? The first and the second, or the first and the third? Please note that we used the word soccer here in the first sentence, but we used the word football here in the second sentence. The third sentence uses soccer again, but it really has a different meaning, right? The first 2 sentences are rather similar when it comes to the meaning, but the third sentence is also about soccer, so it's not completely different, but it has a different meaning. And if we take a look at the results, we see that the first 2 sentences are significantly more similar than the first and the third sentence. See? So OpenAI understands that even if you use 2 different words like football or soccer, it works perfectly fine. The same is true for languages. If you take, for instance, let me show you that example up here. If you, for instance, compare these 2 sentences, the king is dead, long live the king, and der König ist tot, lang lebe der König. Or if you compare the king who is alive is better than a dead one with ein König der lebt ist besser als ein toter König, if I run this thing, you will see that the comparison is pretty high and it has nothing to do with the differences of the characters. Just for demonstration purposes, I calculate the Levenstein distance between these 2 sentences. Again, if you are not familiar with that, Levenstein distance simply takes two sentences and tries to shift around characters and insert characters and counts how many manipulations in the string is necessary in order to get from one string to the other. So it's a structural difference if you want. And you see that OpenAI has absolutely no problem detecting that the meaning of these 2 sentences is the same, although it is written in 2 different languages. So soccer, football, 2 different languages, OpenAI can definitely handle that. Let's take a look at other examples which are even more interesting. Let's take a look at the second example here. He is interested in Java programming. He visited Java last summer. He recently started learning Python programming. Now this is an interesting one because we use a word, Java, in two very different contexts. The third sentence is not using Java, but it is related to a programming language. This is really not a trivial case here. Obviously, sentence 1 is more similar to sentence 3 because both sentences are about programming. The second sentence has a completely different meaning, although it uses the same word but in a different context. And of course, I think you can guess it, the results is exactly that. You see that here the similarities are nearer to each other, but at the end of the day, the distances are significant. 0.535 to 0.587. Again, this has nothing to do with percentage value. This does not say the sentences are 53.5% identical. That's not what we say here. You can only take a look or interpret the values by taking a look at many other values. It's not a percentage value, okay? You will see how we use that later on in enterprise search, for instance. So you see, it understood this. The next one is also a pretty hard challenge for a large language model. Take a look at these examples. I like going to the gym. I want to get fit. I like going to the gym. The next one is the negation. I don't like going to the gym. I'm fit enough. And the last one is particularly hard. I don't dislike going to the gym. It's kind of a double negation thing. So the third sentence is really very similar to the first sentence. The second sentence is the complete opposite, right? However, these three sentences are somewhat similar because they all deal with the fact that we are talking about whether we want to go to the gym. So there should be a distance, but the distance shouldn't be very large. So let's take a look. If we take a look at that one, negation handling, you see that the system correctly identified that the third sentence, which is a double negation, is much nearer to the first sentence than the first sentence to the second sentence. So the negation handling was good. Next example. It's raining cats and dogs. Luckily, not today. I don't know if you were outside, the sun is shining, it's a beautiful spring morning, perfect, or afternoon. The second sentence is, the weather is very bad, it's pouring outside. And the last one, cats and dogs don't go outside when it rains. We have cats and dogs in sentence 103, but I think you can already guess what's going to happen. Obviously, this idiomatic expression, raining cats and dogs, is understood by embeddings. So if I scroll down, you will see idiomatic expressions. You see that the comparison with the third sentence is much lower than the comparison with the second sentence, which simply shows that OpenAI embeddings completely understands the idiomatic expression here. This also works with domain-specific languages. Here, for instance, I have an example that computer was infected with a virus where we use a domain-specific word, virus, in the context of computer science, and then we use viral load in a more medical sense. And the third one, antivirus software, is also again in the context of computer science. And I don't think that I need to show you the results. I don't need to scroll down because you can guess, yes, OpenAI understands that and it works perfectly fine. The last one is way more complicated, and when I tried it, I was really interested in how the system will go about that. It says, I need to get better slicing skills to make the most of my Voron. Now, for those of you who do 3D printing, you probably don't know what this means. Voron is a very, very popular open source 3D printer project. It's an open source 3D printer where you can buy the parts and you can build it at home from scratch. That's a Voron project, okay? And slicing is a very important task when it comes to 3D printing. You essentially need to take a 3D model, you cut it into slices, and this is where the nozzle of the printer will run around on the print bed in order to create something three-dimensional. So here we have some interesting domain-specific words, slicing and Voron. And the second example is you really have to understand what a Voron is. You have to understand that slicing has a specific meaning when it comes to Voron 3D printers. And if you take a look at the second sentence, it says 3D printing is a worthwhile hobby. This is not obvious in the first sentence. And the third sentence is hard because I say, can I have a slice of bread? So we have slicing in there, but it has a completely different meaning. And again, and this time I'm going to prove that to you, domain-specific language works perfectly fine. Here you see that the system correctly recognized that the first two sentences are somewhat similar, not very high, but they are somewhat similar, much more similar than the bread and the Voron example. See? Again, don't take a look at the absolute values. They don't tell you anything. Just the comparison of the two. Of course, I also need to show you the limits. And the next sample was inspired by my wife. She plays jazz piano. Maybe any jazz musicians in the room who you will know what I mean here. The first sentence says, I like how Barry Harris described jazz theory. Now, my wife tried to describe to me what Barry Harris means and what the next sentence means. I didn't grasp it fully. Playing the sixth on the fifth is an important concept that you must understand. Jazz musicians in the room know what the meaning is, but this has to do with musical theory and jazz. And the last sentence is, my friends Barry and Harris often visit me to play computer games. Again, play, see? But it has nothing to do with jazz. Unfortunately, Barry Harris and jazz music is not such a popular concept as 3D printing. So if you take a look at these examples, you will see that the first two examples, which are very closely related for a jazz musician, has a lower similarity than the first and the third sentence. And that's plainly wrong. So if you have, in an enterprise AI solution, if you have a lot of domain knowledge, you can't expect that the system fully understands all your very specific terms. I once worked for a company who does laboratory tests, and the word test has a very specific meaning for them. It has nothing to do with unit tests or integration tests or performance tests. So when they talk about software and tests, they mean something completely different than the rest of the world. I worked for a public company who is responsible for garbage disposal. A garbage collector has a very specific meaning for them, a completely different meaning than a garbage collector in C# in JavaScript or in Go. And again, something like this, you cannot expect that the model understands that. So if you build a domain-specific search solution and you have very specific domain-related terms, you carefully have to test, and maybe you even need to have a fine-tuned model or not a general model like OpenAI in order to train it on texts that are specific to your domain. So keep that in mind. I'm not telling you that OpenAI can work miracles. It is pretty good in generic terms, but there are limits to its knowledge and its understanding. I hope you now get an idea what these sentences are all about, and of course you can take my example and pass in some of your own examples and see how well it works. Good. So let's try to apply this, because now we have the math, we have the embeddings, but what can we do with it? One of the most popular applications of, let me scroll to the slide here. One of the most popular applications of embeddings in the context of enterprise solutions is the retrieval augmented generation, or short RAG pattern. Now, what is the RAG pattern all about? The idea is that a user enters a question, a query, a command, essentially some text. This text is given to an application that you write. This application will not directly pass on the question to OpenAI and say, answer the question. Because probably this question needs to have some kind of knowledge base, maybe a knowledge base which is not public. So OpenAI ChatGPT was never trained with the data. You need to provide your own data, your own quality handbooks, your own internal knowledge bases, your structured databases, I don't know what. So what we do in the RAG pattern, we essentially take the embedding vector of the question and send it to a very special database, to a database which is capable of doing a vector search. So what we essentially do is we take a large body of documents, maybe from your, I don't know, from your SharePoint or from your Confluence wiki or from PDF documents which lay around in your document management systems, I don't know. And you take these documents and you calculate a lot of embeddings for every single document and you store them in the database. So you have millions of multidimensional, high-dimensional vectors in a vector database. And then you take the question, the embedding vector of the question, and you do a nearest neighbor search. You give it a vector, embedding vector, and you say, find me the 10 nearest neighbors of these millions of vectors that I have in this database. And this is exactly what vector databases are all about and where they are really, really good. They can create indexes over lots and lots and lots of vectors, and they are very fast in finding the nearest neighbors in a short amount of time. What you currently see is that a lot of existing databases like Azure Search or Postgres or Cosmos DB or SQL Server, they are learning capabilities, vector search capabilities. But there are also specialized services like Pinecone or Quadrant and many other services out there in the public that are capable of storing and retrieving those documents based on a vector search. Now what we then get back in the application, we get the seemingly most relevant documents from our database. That are those documents which have the highest cosine similarity compared to the question that the user entered. And last but not least, you take all these documents, put them into a prompt and say, hey ChatGPT, this is the question of the user. I have here some documents. They probably contain the answer to the question. Please go through it and create a meaningful response. So at the end, we use ChatGPT for generation. And this is why it's called retrieval augmented generation. Because we use a retrieval tool based on vectors and embeddings to augment the generation, which is done using a tool like ChatGPT. And this is exactly what we are going to take a look at in the next example. Because I only have 1 hour in this presentation, I am not going to use a vector database. Maybe this is something for the next OOP conference. We'll see. Today we are using the memory of our Google Colab as our vector database. What I did is, with the help of ChatGPT, I'm not very creative if it comes to this. With the help of ChatGPT, I created for a fictitious travel agency, I created 10 different holiday vacation spots. Like, I don't know, Aurora or Cinder Peak or Windmere. You can take a look at the sentences. It's not very relevant. You do not need to read them. Let's simply store them in an array. So here we are just storing the documents in an array. This would be your document database. Got it? This would be your Confluence wiki or whatever. Now we need to fill the vector database. And how do we do that? We go to OpenAI and ask it to generate the embedding vector for every single document. And we are going to talk about document pre-processing in a second, okay? But for this example, I just went through the 10 holiday spots and calculated the embedding vector for all these 10 spots. That's all what I do. I simply store it in a vector in memory. And now I create a query. My query is, for vacation, I want to go hiking in the mountains. I want to really feel nature. This is my query, and again, I'm calculating the embedding vector of my query. Let's run it. Now we have the embedding vector of the query. By the way, calculating embedding vectors is blazingly fast and very, very, very cheap. I can't tell you how many zeros are after the comma when you express it in euros, for instance, per 1,000 tokens or something like this. So it's really doable to calculate the embeddings for a large number of documents. You will not spend a fortune for that. Don't worry. It's way less expensive than doing ChatGPT calls, okay? You can take a look at it. The link to the pricing document is in my Google Colab. Now, we need to identify the embeddings. And what I do here is I'm calculating, you see it here, the dot product between the vector of the query and the vector inside the database. This is the cosine similarity. I showed you the math before. The cosine similarity is simply the dot product because all the vectors are normalized. And I'm using a Python library called NumPy, which does it pretty well. It's capable of multiplying multidimensional vectors pretty fast. And then I am going to sort this thing, as you can see it here, I'm going to sort this thing so I get the most relevant documents on the top. So I take the cosine similarity and get the documents ordered. This would be a k nearest neighbor search. Give me the 3 documents, the 5 documents, the 10 documents which have the highest cosine similarity compared to the input. Good, let's run this guy. And just to show you, the first one says Aurora, a serene mountain city hidden in misty peaks with ancient monasteries and breathtaking hiking trails. So you see, that is perfectly fine to what we asked the system for, right? So let's visualize the result. I wrote a little bit of Python in order to visualize the result, and you will see that Aurora is by far the most relevant text document in this query. And a k nearest neighbor search, with k being 3, would result in these 3 documents. So what can we do next? Next, we invent a prompt for ChatGPT, and this prompt says, you're a helpful assistant in a travel agency, blah, blah, blah. Make suggestions based on the city descriptions provided below. And now comes an important one. Only use the provided city descriptions. Do not use other information sources. Additionally, I tell the system, if you cannot generate a meaningful answer based on city description, say, sorry, I cannot help. If the user's input is not related to finding a travel location, say, sorry, I can only help with vacation locations. And here, we insert the documents from the vector search. And this is the generation part. So now we finish the vector search, we inject the documents, and now we do the generation. Let's run it. You see, this is the prompt. Aurora is number 1. Maybe we could have told ChatGPT that we think that the first one is most relevant, but you see ChatGPT answered perfectly. Based on your interest in hiking in the mountains and feeling close to nature, the city of Aurora would be an excellent choice, and so on and so on. So, it did a pretty good task. Let's try 2 or 3 other examples so that you see this was not a fluke, it really works. For instance, if we say, in my vacation I want to party, very different from going back to nature. Now let's do the vector search, doing the dot products and so on. I will not visualize the result, I think you can guess that. And I will run this generation part with ChatGPT, and now the system tells me that for a vacation focused on partying, I suggest you visit Vespera. It's a city that never sleeps, with a vibrant nightlife and cultural festivals that will keep you entertained. Perfect. This is exactly what we wanted. Now let's challenge the system a little bit. Let's challenge the system and tell the system we want to travel to an underwater city. Unfortunately, there is no underwater city, at least not in the vacation list that we have here. So let's do the calculation. Don't get me wrong, the system will still look for the most relevant documents because it doesn't know at that point of the search that there is no underwater city. And what we get back as number one is an island city with a rich maritime history. This is not an underwater city, but at least it is an island. Okay? But then we have ChatGPT. So what we can do is we can run that through ChatGPT, and hopefully ChatGPT will be intelligent enough to say, sorry, I cannot help. And that is exactly what I told ChatGPT to answer in the case that it doesn't have a suggestion. In real life, in a real travel agency, it will probably be a little bit more polite, but I think you get the idea, right? And last but not least, let's take a look at my last example. The last example is, what is the name of Bart Simpson's sister? And again, the system will of course do its very best to find relevant documents. Maybe we can travel to the hometown of Bart Simpson, I don't know. But if we run ChatGPT, then ChatGPT will say, sorry, I can only help with vacation locations. In real life, you would probably do it the other way around. In real life, you would probably, before doing the vector search, take the query and ask a ChatGPT model, is this query travel related? And if ChatGPT immediately says no, that has nothing to do with travel, you will probably not even do the vector search. But this is an optimization that is very project specific, and you have to come up with your own solutions in that area. This has nothing to do with embeddings or vectors. Good. Now the problem that we have when we want to build examples like that is that even the new models, they are very limited when it comes to the number of tokens that those models can process. It's roughly 8,000 tokens that the embedding endpoint of OpenAI understands. A token is approximately in the English language 4 characters. So we have somewhere between 25 and 30,000 characters. If you have long documents, they will probably be longer than this number of characters. And it's also important to have rather small documents for the vector search, because remember, the documents will be injected in a ChatGPT prompt. And how do you pay for ChatGPT? Based on the number of tokens. So if you always put large documents into the generation part of the whole solution, you will pay a lot of money to OpenAI. They will be happy, you will not be happy. So what you want to do is you want to have a much finer structure. You want to split your documents into small chunks and then do the vector search based on these small chunks. Because then your prompt will be small and your system will be less expensive. But how? How can you split the documents? I'm not talking about technical details, how you can get the text out of a PDF document. That's a problem that is solved. Trust me, that is not too complicated. Yes, this is something that developers have to code, or you have to buy components or systems that do the transformation, the technical transformation. But this is something that developers like me love to do. Yeah, that's a technical challenge, we know how to do it. However, the problem is more of a linguistic one. Let's take a look at this example that you see here. Imagine that we have a document with these two sentences appearing right after each other. The first one says, VX2000 requires regular lubrication to maintain its smooth operation. Next sentence, the machine requires the DX97 oil as specified in the maintenance section of the manual. What we have here is a so-called anaphoric connection. In German, anaphorische Verbindung oder anaphorischer Link. What we have here is we have the model of the machine. It's a fictitious machine, it doesn't exist. And here we have the machine. And this is an anaphoric connection or anaphoric link between these two sentences. Now, if you naively split your document after, let's say, 1,000 characters, it can easily happen that the second part of the anaphoric link is in one document, and the first part, which is relevant because it has the the machine's name in it, is in another document. And therefore, the cosine similarity of a user query that contains VX2000 will be much lower in the second part of the document, because it doesn't say VX2000. Maybe even worse, what happens if there is a different document that has a similar structure, but it talks about a different oil with a different machine. And then suddenly bad things can happen because the cosine similarity might run into very wrong underlying texts. So you see, splitting up these documents is not a pure technical problem. So if you have, sometimes I see that, if you have suppliers telling you that you just have to throw in all your PDFs and they will magically split everything and solve all your problem, it's simply not true. You really have to take a look at the documents, and sometimes you need to understand how these documents are structured. Now let me show you some examples to make it more relevant. Here you see that I take this sentence here, what oil is recommended for VX2000, and in this case I am having such an anaphoric link. Here in the first example it says the machine. In the second example it's the same content, but we say VX2000. So we removed the anaphoric link by duplicating the name of the machine. How did I do that? I will show you that in a second. First, I would like to show you that the result is really important, because if I scroll down here, you will see that the one with the anaphoric link has a cosine similarity of 0.472, and the next one has a cosine similarity of 0.692. That's significant. The content is exactly the same. We just removed the anaphoric link. And how did I do that? Well, you can do that with BioBrains by simply hiring people rewriting your documents, or, of course, you can ask ChatGPT to help you. And what I did here, and the link is in my document, I simply took the original text, which is fictitious, it doesn't exist in real world, and asked ChatGPT to rewrite the following text to remove anaphors. It understands what it has to do. And it rewrote the document automatically. So what I got was this difference. I have it here in a diff checker. I guess you can't read it from the back, but maybe you can roughly guess that here we have the machine and here we suddenly have the VX2000. So what you can do is you can use AI to pre-process your documents, or you use BioBrains if it's too complicated for the AI. Good? So this is one thing that you have to keep in mind. The second example is one that is a little bit different. You see, here I have a document which talks about maintaining the safety cover. We have the same machine, VX2000, but there is a version of the VX2000 that has a safety cover so that nobody can reach into the machine and get hurt. Okay? Now the question is, I have a VX2000 SC, stands for safety cover. Can I remove the cover to work faster? Obviously, if we only take a look at this document, the problem is again that we don't see the VX2000 SC, but this is not an anaphoric link. The problem is that in this document, we simply lost the top level header. This is markdown. So this would be the header 1. This would be the title of the document. The name of the machine is simply specified in a header way more up in the document. Understood what I mean? So if you split the document by paragraph, for instance, you lose context, because you don't have the headings. Now what you can do is you can pre-process your documents to manually or automatically inject the parent headers, or maybe some document metadata or document keywords, or whatever fits to your needs in your specific project. And that again is very important, because as you can see it here, the cosine similarity rises significantly just by adding the additional header number 1. Only by adding the header. So it's way more likely that your RAG pattern will detect this document now than it was before. And the last example is, I try to have a little bit of fun. What would you say if I give you only, if I give you only, where's my notepad? Let's take this one. Yep. This text. In ensuring the optimal functionality and longevity of the bed, one crucial aspect often overlooked is the tightness of its screws. When these screws are not sufficiently tightened, the bed can become the source of unnecessary noise during usage, as the bed may wobble or shift. Now, what comes to your mind? No, I don't want to know it. I really don't want to know it, what comes to your mind. And now I'm going to show you the real world. Again, it comes from a hobby of mine. It comes from a Voron assembly manual. And now you know, maybe if you're a 3D printer enthusiast like I am, you know that we are talking about the print bed. The print bed is the surface on which the printer prints the 3D model. So it's super important to have this context. If you would simply, naively split the document at the wrong position, the AI might deliver some very wrong results. I think this example drives the point home, and if you take a look at the example, well, both are about beds, so the difference is not so large, but still it is significant. So the chance that we get the second text correct is really much higher. And that is exactly what I wanted you to know and what I wanted to show you. My goal was to give you an idea how these embedding work. I wanted to show you how they are applied in enterprise AI solutions. I showed you the math with the cosine similarity. I showed you new things that happened the day before yesterday, and hopefully the examples showed you made it easier for you to get a deeper understanding of what embeddings are and what the RAG pattern is. I want to thank you for your attention. I said I wanted to finish early. We still have 5 minutes, so I'm more than happy to answer your questions if you have some. Thank you very much for coming. Enjoy the rest of the OOP conference, and now it's time for questions.